Live. All right. Hello, everyone. I'm gonna get started. Thanks for all coming. Hope you guys had like a good homecoming weekend so far. This is gonna be a continuation off of Crypto 1 from last time. If you didn't catch that, then recording is up. I would also say if you're in the Discord, if you're on the Discord, join the Discord, and if you're in the Discord, download the slides because there are some more links and stuff in the slides if you want to learn more about some of the things I'm talking about. But yeah, let's get started. So just as a quick outline again, we're going to go over the Chinese remainder theorem. Then we're going to go over elliptic curve Diffie-Hellman. And then we're going to cap it all off with an introduction to asymmetric encryption using RSA. So all that sounds good. The only announcement is, just like I said last time, afterwards, we're all going to be heading over to ACM to do hopefully the final round of ACM cleanup. And from that, the ACM room should be happy, should be all good to go for both DDR and Halloween party that ACM is planning soon. Yes? I just want to say thank you, everybody. Y'all made such a huge difference that we got others. I would love everybody. Yeah, it'll be great. All right. With that, here's the XKCD and here's the flag. I'll give you guys some time to copy that down. Rivest, Shamir, and Adelman, RSA, are the founders of the RSA Cryptosystem. So we'll get into that. But yeah. Have we used an XKCD at every single meeting? Or there's too relevant. All right. All right. If you didn't get the flag, slides are posted, so I'm gonna just move on real quick. Everyone good? All right. Cool. The Chinese remainder theorem. What is it? Why do we care? So hopefully you all remember modular arithmetic from last time, or you've seen it in your courses, right? We're looking at values mod some number. We're looking at remainders after division. And because of this, there's this little aspect that we lose information. But what do I mean by losing information? Suppose I tell you to find 4 times 4 mod 3. Well, that's 16. 16, after I divide by 3, I get 5, remainder 1. So the result is 1. It's the remainder. Now imagine you didn't have that from before. And I said, okay, you know x is equal to 1 mod 3. And I tell you to find x divided by 4. This is harder. It's not obvious what x is, and you don't really have a good way to figure this out without just trial and error. Yeah. There are also multiple answers. Yes, this is a very key point. So yeah, going forwards is easy, going backwards is hard. But let's look at another example with a larger modulus. So again, let's say I tell you to look at 4 times 4, but this time mod 20. Well, now we will know that the result is 16. If I take 16 divided by 20, I get remainder 16. And now if I tell you that x is equal to 16 mod 20, then I told you to find x divided by 4, then you would know the answer is 4. It's much easier because 16 divided by 4 is 4. So we have this difference between using a small modulus and a large modulus, 3 versus 20, and this generalizes to just small numbers versus large numbers. We can actually take advantage of this fact if you have multiple equations for doing modular arithmetic. So this is the Chinese remainder theorem. The Chinese remainder theorem gets its name because it first appeared in ancient Chinese math texts dating back to the 3rd century. So let's just try to find x such that x is between 0 and 105. And we're given the following information, okay? So x is equal to 2 mod 3, 3 mod 5, and 2 mod 7. With just this information, since 3 times 5 times 7 is equal to 105, we can actually find the unique X in this range, right? And this is what the Chinese remainder tells us. Now we can find that X is equal to 23 after doing mod 3 times 5 times 7, 105. So we know X is equal to 23 mod 105, even though we were only given the remainders after division by small numbers. And the Chinese remainder theorem, if you look into it, will tell you how to find such a thing, or there's also a Chinese remainder theorem function in various math libraries, including SageMath. So this is how you would do it. And just more generally, right, when can we do this? Because in CTF challenges, before you apply an attack, you should know that the attack actually is valid. There's no point throwing a bunch of compute power at something without knowing it's valid. Otherwise, you'll be waiting a while. So anyways, so suppose if we have X is equal to all these n's, n1, n2, all the way up to, let's say we have k equations. And let's say these are all mod p1, p2, pk, such that each pi and pj, when they're different, they share no common factors. They're co-prime. If these share factors, then the Chinese remainder theorem doesn't apply. So if we have these conditions, then we can find a unique X mod P1 times P through P2 all the way up to PK. And so this allows us to gain new information just given these smaller pieces of information. Yeah, you can look into the proof for how you actually do this. It's really interesting. But if you're just doing this like on a computer, then I will look into Chinese remainder theorem functions from places like SageMath, right? So why do we care? Well, basically, any cryptographic system that we've been looking at, so Diffie-Hellman, soon we'll be looking at RSA, and basically any other crypto system, they deal with modular arithmetic. And since this applies to anything with modular arithmetic, this shows that we have to be careful with choices of primes that we use in the cryptographic system. So where this really comes up is when we consider what we call smooth primes. So obviously, primes have no factors other than one and themselves. But if we take a prime and subtract 1, and we look at the factors of p minus 1, and let's just say p minus 1 has a lot of really small factors, right? So even if p minus 1 is very large, it can be factored into a bunch of small primes. Well, then there's an attack called Polig-Hellman, which allows us to gain information about certain like modular equations using small primes. Yes. I do not know large primes off the top of my head. Huh? These are not that big. Those are not small. Those are, well, they are primes. They're no, because they're very small. Smooth primes are typically like very large primes. Yeah.
So smooth is like the topic that you're looking.
Yeah. The point is like yeah. So like these really come up when you have primes which are like 20, 21 digits, like quite large. So I don't have these memorized. Sorry. Yeah. Yeah, smooth primes are very vulnerable to Polig-Hellman, which is based off the Chinese remainder theorem, right? And some of you, if you've been looking into security for a little bit, you may have heard about something called logjam. And logjam was when a bunch of security researchers basically crawled the internet and looked at TLS and SSL traffic. Even though TLS and SSL is typically encrypted, they were actually able to take advantage of the Chinese remainder theorem and Polig-Hellman, since most crypto systems used in the real world use the same primes. They just like look up an implementation and like, oh, they're using that prime, must be good, I'll use it. This happens a lot. If you look at like the National Institute for Standards and Technology, I think is the NIST, they will recommend certain primes and stuff. So then a lot of people end up using them. And these researchers took advantage of the Chinese remainder theorem, used this attack, Polig-Hellman, and were able to leak information about encrypted traffic.
All primes given by No, so
A lot of places, yeah.
I think it's like a mathematical attack.
Yeah, it's just
You could substitute your own parameters.
yeah, there's some more work that happened with it. They just straight do Chinese remainder theorem. But the Chinese remainder theorem was at the center of an actual like attack that people did in 2015. It's really cool stuff. That link leads to a really nice write-up by the people who did this attack. I highly recommend it. But actually, yeah, before I move on, does anyone have any questions about this stuff? It's like Chinese remainder theorem before we and like see and like how it can be used in an attack and all other things. All right, cool. So now that we have like this tool under our belt, we can now attack basically any system that uses smooth primes. I have a couple challenges on that. And using smooth primes, you can do this attack. And yeah. So now, moving on from that, we're going to look at another form of Diffie-Hellman. So if you remember Diffie-Hellman from last time, we were just using numbers, right? So let's just look at the old and the boring normal Diffie-Hellman. All right, this is going to be a quick review from last time. So we have some generator G and some prime P. And using this, here's what our two characters, Alice and Bob, do. Alice and Bob each randomly choose a number between 2 and P minus 2. Okay, and these are their secret keys. Using this, they compute, so Alice computes G to the A mod P and gets a public key, which we'll call capital A. And Bob does the same, computes G to the little b mod P, and we get capital B, Bob's public key. And then over open internet traffic, they send A and they send B. This is all secure because if you remember from last time, finding little a and little b is what we call the discrete log problem, and it's really hard to do. We believe there are no polynomial time algorithms to do this. You have no better chance to get A and B than just brute force. And now Alice can compute capital B to the little a, and Bob can compute capital A. No, Alice can compute capital B to the little a, and Bob can compute capital A to the little b using the information they received and their private information. And if you remember from last time, just because of how exponents work, they end up with the same shared secret. And no one else has this because remember, Alice's information is little a is private and Bob's little b is private. But who says we have to stick with just regular numbers or just normal modular arithmetic? So there's this thing that we call an elliptic curve. I'll show you some examples later, but these are quite literally curves that you're used to seeing in classes, like normal, like y equals something, or in this case, you're gonna have y squared equals something. But the point is, it's just a curve on a 2D plane that we've all seen in many, many math courses. So the curves take this form of y squared is equal to x cubed plus ax plus b. And actually, the reason they're called elliptic curves is, I think maybe like about 150 years ago, mathematicians were really interested in looking at formulas for the arc length of an ellipse. So this is much harder in general than looking at the arc length of a circle, which you guys may remember from calculus or geometry. Doing this for an ellipse is quite hard. And it turns out when you start looking at formulas for this, equations of this form, y squared is equal to x cubed plus ax plus b, these equations come up a lot. And so the name elliptic curve is stuck around. But now it's used for way more things, including cryptography, as we'll see from here. So this is just an example of what some of these curves look like. It's not important that you can recite off the top of your head, like, oh yes, if A is equal to 1 and B is equal to 2, this is what the curve looks like. But I guess like the point is that you have this general shape where you have like this around like the origin, you have this more clustered part. And as you get away from the origin, you have these tails that go up to positive infinity and negative infinity. And if you look more towards like the right-hand side of this table, where you don't have like this little circle or even lack of circle, those ones on the right are what we use for elliptic curve cryptography. Having that little circle on the left hand leads to some attacks, really complicated attacks. We're not going to go over that today. But the point is, your curves are these curves are kind of complicated to look at. But we're doing cryptography, and so we need some way to add, multiply, do exponents or whatever. How do you add and multiply when we're, instead of dealing with numbers, we're dealing with curves? Well, we'll break this down. This is a couple elements, right? So in general, if you look in the bottom left, if we have 2 points, P and Q, and we want to add points on the curve, what we do is we just draw the line going through the 2 points and then calculate its next intersection on the curve. And for various reasons, this next intersection is always guaranteed to exist. And because of that, we grab that intersection and then we project it down the other axis, or if the intersection ends up being below the axis, we project it up. And the whole point is that's how you get P plus Q. And this operation works like normal addition, right? You can add points in any order, you can switch the order you add them, you can group them in any way. It works like normal addition. It's just that now we're doing with points on a curve. If you want to subtract a point, so or actually before we get to subtraction, if you want to take 0, so the analogous element for 0, right? So P plus 0 is itself for any number. Well, what we do is there's a special point at infinity, so it doesn't exist anywhere on the curve, and you take P plus the point at infinity. Usually when you program, we just denote it as infinity, and there's just a little lookup, if infinity, return the original point. If we add a point at infinity, we get the original point back. So now we can add things, and we have a number called 0. If you want to subtract, we just look at the projection across the x-axis, and this is our subtraction. And if we have this, so we if we subtract a point, we just go across the x-axis. And if we want to double the point, well, we're adding a point plus itself. We can't draw an intersection. So if you think about it, these points get infinitely close together, and the intersection of the point with itself ends up being the tangent line. So you look at the tangent line and where that intersects, and then project it down, and you can double. And since we can add and we can double, we can subtract, we can basically use these operations to now do cryptography, where our objects are now points instead of numbers. Does this all make sense? Does everyone kind of understand like the universe of things we're playing with right here? All right. So just a quick side note. These curves, as I've been showing you, exist over real numbers. So here's a different curve, right? And if I have real numbers as my inputs and outputs for x and y, I get this nice smooth looking curve. But it turns out that if you limit yourself to this, there are actually it actually ends up being really, really hard to do cryptography. You can't really use actual real numbers in a computer just because real numbers are infinitely long, technically, and we have certain size limits for like floats and doubles and all that. Point is, can't really accurately represent a real number, and they actually turn out to be insecure for a number of reasons. But what we do is we instead, just like when we were looking at the Diffie-Hellman before, instead of working with real numbers, we work with integers modulo some prime. Okay. So what this looks like, right? If instead of having continuous points, now I'm just going to have just isolated points all over the place that represent integer coordinates that are on this curve. And if you end up plotting this, you get this, which you never have to look at when you're actually doing this. But the point is, what I'm doing is I'm just taking the points on the curve that are integers. I'm just doing mod, and I'm just applying the mod, in this case, 89. And what I get is I just get this essentially random-ish scatter of the points. It ends up being symmetric across the x-axis, because as you remember, every point has this negative below it. So you have this vertical symmetry. But otherwise, for all intents and purposes, this is essentially random, right? And this actually leads to some nice security properties. Yes. there are like algorithms where there are algorithms to kind of do this fast, but really, so you know that you're dealing with numbers mod 89. So what you do to check this is you try every x from 0 to 89 and every y from 0 to 89, plug in those pairs to the equation. If you get equality on both sides, then that point exists. And since we're only looking at integers mod 89, that's a finite number of points, and we can just enumerate through it quickly. So if you know the curve, you can enumerate through the possible points. That makes sense? Right. Mm-hmm. Yes, that will always exist. It is kind of counterintuitive that like when I look at just integers, why does it always exist? But I don't remember the proof off the top of my head, but it just turns out that the numbers do work out. If you look at the actual arithmetic, yeah, it's essentially, I'm not showing the proof because the proof is just take the operation and do the algebra. I don't want to walk through just doing lines and lines of algebra. You don't want to see me walk through doing lines and lines of algebra. You can look it up. It's quite cool, but it is essentially proof by the numbers work, which we're very thankful for that the numbers work. All right. So if you remember with the discrete log, right? So we looked at normal logarithm versus discrete log. Normal logarithm had real numbers. Now we're looking at the discrete version. Well, we have this. So given G and capital A and a prime P, find little a such that G to the A is equal to capital A. And for various reasons, we believe that there is no better way to do this than just brute force. Try A equals 1, then 2, then 3, then 4, all the way up. And if P is large, and typically primes when we do cryptography are quite large, 256-bit, 512-bit, and even a recommendation is starting to tend towards doing 1024 bits and 2048 bits. These primes are large. You cannot effectively do brute force. But what's the equivalent discrete log problem for elliptic curves? So let's start taking a look at that. So now, instead of numbers, we're looking at points. So we have a point capital G, which is our generator, so analogous to little g from before, and a point capital A, which is analogous to capital A from before as well. And again, remember we're doing this modular arithmetic stuff on the points, so we need a prime P. So we're going to find a little a such that if I multiply G with little a, and analogous to, I want to find capital A. And this multiplication by a scalar is analogous to multiplication in like normal numbers. If I look at 4 times 3, well, that's 3 plus 3 plus 3 plus 3, 4 times. And it's the same thing here. If I look at some scalar, little a, times capital G, well, remember, we can add points together, right? So if a is 3, that's just going to be capital G plus capital G plus capital G. It's the same problem. It's just like the same operations, and now we need to look for this little scalar. And we also believe that this problem is extremely hard for large primes, and specifically for curves that have many points on them. And because of this, we believe that this discrete log is hard. And so if we have a hard discrete log problem, can we do Diffie-Hellman with it? Well, yeah. So before looking at Diffie-Hellman, why is this hard? Okay. Let's just think about the game of pool. So when I'm doing pool, right? If I say, okay, I'm going to hit the cue ball into this other ball, and I want to find where the ball ends up, in the pocket, whatever. This is easy to do. I can just do it and see where the ball ends up. This is analogous to doing exponentiation or multiplying a point by a scalar, right? I can multiply a point by a scalar and see where it ends up. This is easy to do. But let's look at the reverse. Here's a bunch of points on our plane, or in this case, balls in an 8-ball game. And I tell you, okay, can you tell me where these balls started like in the position prior. Can you tell me where they started and how hard we hit them? We can't do this. This is really, really hard. We can't just reverse time. We can't find where these balls started from if they initially started from some random configuration. And it's the same kind of logic that applies to why elliptic curves are secure. If I just point at a random point on the curve, and I said, okay, I took this generator point, multiplied it by some random number, and I ended up here. There is no inherent relation between our target point and the starting point. Similar to how, if we don't know how hard we hit the cue ball into another ball, we don't finding the starting position given the ending position is hard. This analogy kind of makes sense. Can we kind of visualize what this will look like on an elliptic curve with essentially the points kind of bouncing around all over the place as we add it to itself? All right. So again, let's take a look at this for normal discrete log. Elliptic curve Diffie-Hellman is going to look very, very similar to this, but there are going to be some slight changes, right? So we're going to take this. Now let's look at the elliptic curve Diffie-Hellman protocol. So again, we have public parameters, right? So the curve, when we do this, is public. If Bob and Alice have to know what the curve is, there's just like no way getting around this. So we have the curve, and we have the generator point, G, and the prime, little p. And we're going to do all the math mod p, as I said earlier. And we now have this new value we need to look at called the number of points on the curve, which we denote as pound e. And this is just notation. You can count the number of points on the curve, given the curve. So instead of Alice and Bob generating integers between 2 and p minus 2, now we're going to generate integers between 2 and the order of the curve minus 2, right? So the same thing, we're looking at essentially options for what we can use as our scalar multiple. Then, similar to normal Diffie-Hellman, Alice and Bob are independently going to calculate the generator point times their secret key. And then they're going to send it to each other. Still very similar to Diffie-Hellman. This is Diffie-Hellman. And then from this, they're going to compute their shared secret. And similar to how their private keys were known only to them, reversing this shared secret is really hard to do. So does this make sense? Yes.
How do you start it's in the approximation.
You have to have it precise. It is okay for this number to be public. So essentially, when you do this setup, we assume that this was computed offline somewhere.
There's a polynomial.
Yeah, you can. There's a polynomial time algorithm, but you essentially just compute it. Yeah.
Next question is there a fast forward like algorithm for like calculating this pound E is so large?
Mhm. Yeah.
Is it no faster than that?
There is a faster way using an algorithm which we call doubling and adding. And so we can double points and we can add points, right? And the way we do it, so let's say I want to compute, just for a small example, 5 times g, okay? Instead of doing g plus itself, actually, let's compute 9 times g. That'll be a better example. Instead of computing g plus itself 9 times, which takes about 9 operations, I'm going to take g, double it, get 2g, double it, get 4g, double it, get 8g. And I have 8, and then I have 1, and I can add it together. And this scales up really, really nicely to very large constants. And I didn't write out the algorithm here, but the algorithm is called doubling and adding. And I believe this is also like what Sage Math and Python do when calculating exponents. They do doubling and adding to make it faster. But that's the inherent idea. So that's why we specifically want to be able to double points and add them. But yeah, if you're interested, the algorithm is called double and add. I thought someone else had a question. Yes. So if like little a and little b are 1, then a is just going to be g itself. And then so if Bob got Alice's point and saw it was the exact same as the generator, then Bob would know, oh, Alice's secret key is 1. So we omit 1 to get rid of that. And you could, I guess, extend this similarly to like, okay, we can omit 2 and other small values because Bob could just cache these. But if pound E is very large, there's not really, you can't really just store this value because the numbers get really big. And we do this especially on curves, which like the order is like of like the, I think, hundreds of thousands. So it becomes inefficient to store this. And we omit pound E minus 1 because for various reasons, this ends up being, again, a very simple to compute value where if you get Alice's point and you know it's a specific value, it ends up being the inverse, I believe, of the generator, then you would know Alice's secret key. Yes. Yeah. Yeah, I think these are usually on the orders of like, correct me if I'm wrong, like hundreds of thousands of points, right? But yeah, hundreds of thousands and millions. Really?
So the Bernstein curve,
Uh-huh.
the most common curve that's used, not most common, a common curve that's used is curve by made by Daniel Bernstein. And it has, just looking at the Wikipedia page, like on the order of 2 to the 2.5.
Oh, okay, yeah. Yeah.
So there is no way.
Yeah, 200, 255, but yeah. I guess, yeah, that makes sense. It would be that. It's similar to like actual cryptography where if we're doing actual numbers, we look at 512-bit numbers and 1024 and 2048 because caching that you cannot on your normal computer. Like 2 to 256, yeah.
More points than you can.
Yeah, essentially. And then I thought someone here had a question. Did you? Oh, okay. All right. All of this makes sense, right? And so, actually, before I move on to RSA, I'll just talk a little bit more about attacks on this. A lot of the attacks that work on normal Diffie-Hellman work on elliptic curve Diffie-Hellman, but at much smaller scales. So I think off the top of my head, if I have a 512-bit normal Diffie-Hellman system, it's about equivalent to a 128-bit elliptic curve Diffie-Hellman system. So since the numbers are smaller, it's much more efficient to compute because we're doing these operations a lot when we're doing cryptography. And so we want it to be relatively efficient. And since it's relatively efficient with smaller values, you see elliptic curves used a lot. You can actually compute elliptic curve SSH keys to use for various things like Git and SSHing into other servers and all these things. It's used a lot because with smaller key sizes, we can gain same security with more efficiency. Yes. They are kind of, but it doesn't really matter as much. The main thing we want to avoid, which is so the analogous property of smooth primes for Diffie-Hellman. The analogous thing is when the number of points on the curve -1 is smooth. When that's smooth, it ends up being, there are very similar attacks. I think it's yeah, it's the number of points. Yeah. Is that -1? It is minus. Okay, fine. The number of points on the curve. Yeah. No, if it is smooth, it is problematic. Yeah. Again, because it's still modular arithmetic. It's still like doubling. Like the objects we're doing the math on are different than actual numbers, but it's a lot of the same fundamental operations. So in fact, Chinese remainder theorem applies. It's just with a more complicated object. But all like the actual like, Chinese remainder theorem, that result is perfectly analogous to doing it on elliptic curves. So for the same reasons, you get the same attacks. So yeah, so if you see elliptic curve challenges and you factor the number of points, which again, Sage does all of this for you, by the way. Like there are like elliptic curve like classes and functions and stuff where it will do all of this for you. So it'll compute the order of the curve, and then after you compute the order of the curve, you can factor it using Sage's factoring tools. And if you see it smooth, then you know that okay, certain attacks will work. So yeah. So this really caps it off for Diffie-Hellman. This is kind of like normal Diffie-Hellman, elliptic curve Diffie-Hellman are like the things you'll see in challenges and like what's used in real life. There's really there are generalizations of elliptic curves called isogenies, which we don't use for normal computers, but actually very recently isogenies were like hoped to be the big forefront of like yes, post-quantum cryptography. And it was found very recently that isogenies don't work. So I was actually talking with someone at Microsoft Research whose whole research field was using these special elliptic curves for post-quantum cryptography. And I was talking with him, and he's like, yeah, 8 years of my life's work just kind of went down the drain. This is the reality of cryptography, where you can sink your heart and soul into a crypto system, all for someone to look at it and be like, wait, this is insecure. And so I feel bad for that guy. But but yeah, for normal cryptography, because none of us have quantum computers yet, this is kind of like the state of the art. This is what we use. Yes. I hope you of all people don't have a quantum. All right. Are you all good with Diffie-Hellman and symmetric encryption? All right. So now we're going to look at RSA. So RSA is different than previous encryption we've seen. Instead of looking at Diffie-Hellman and XOR, which were symmetric, let's look at asymmetric encryption. So rather than a shared secret key that both parties have, we can have a public key and a private key, which without sharing any other information, anyone can use a public key to encrypt the message, but only we can decrypt the message. So if you think about what happened with XOR and Diffie-Hellman, both parties to send and receive messages have to know the secret key. With asymmetric encryption, the sender does not have to know the secret key. Only the receiver does in order to decrypt the message. So there's this asymmetry that goes on. And RSA is one such asymmetric protocol. So just a very quick detour. There's this thing called the totient function, right? And you don't really have to know the specifics for how this works, but what it is the number of numbers greater than or equal to 0 and less than n, I forgot to say, that share no factors with n. And the important thing to know is that if we take any number that doesn't share factors with n, raise it to this special number, we get 1. And the fact that this works, there's a proof linked on the slides. It's really cool. If you know this, then using this is the basis for this entire RSA crypto system. So at the center of Diffie-Hellman was the discrete log problem. So now we need an analogous hard problem for RSA. So multiplication is easy. We all know this. We can just plug in 2 numbers into a computer, multiply it, we're all good. Factoring is hard. So we again have this easy to go forward, hard to go backwards thing. I give you a really big number, factoring is really, really hard. So when looking at RSA, we consider 2 large secret primes, which we'll call P and Q. And I'll multiply them together and I'll get n. N is public, but if I just give you this really large number, again, on the order of like 1024 bits to 2048, factoring is really hard. Your computer will not be able to factor and find P and Q. And turns out that this totient function ends up being p minus 1 times q minus 1. So you don't really have to know what the totient function is. Just know if you see that symbol phi of n, it's p minus 1 times q minus 1. All right, that's all you need to know. But it's hard to find p minus 1, q minus 1 if you don't know p and q. So if I just give you n and tell you to find phi of n, you're not going to be able to do it. Because, like I said, factoring is hard. And thus, since factoring is hard, finding phi of n is hard. So let's look at how RSA works. So we have a public exponent, e, and usually for just because it's a really easy value to compute because binary, e is usually 2 to the 16 plus 1, which is large enough that we get security, but for this public exponent, this is a value everyone knows, but it's large enough that we get security, not so large that doing math with it becomes really hard. And so what Alice does is Alice is going to generate large primes p and q. Then Alice is going to calculate p times q, get n, and release it as a public key. Then Alice alone is going to compute this p minus 1 times q minus 1. The rest of the world can't do this because, again, to compute this, you need a factor n, which we said is hard. But Alice knows p and q. Alice generated this. So we're all good. Alice can, and this phi of n is the private key. So we have this public key, private key paradigm. Knowing this, we can compute this number d such that e times d is equal to 1 mod phi of n. And if we have this, we're able to use this d, which is a secret value, as a private key as well. You can actually compute this really quickly using what's called the extended Euclidean algorithm. I'm not going to go into the details for it. There's a nice write-up on Wikipedia for it. But the point is, if you know the private key, this is really fast. If you don't know the private key, you cannot do this. You cannot do this given just n and e. And so if Bob wants to send a message to Alice, so Bob is the sender, all Bob has to do is take the message and raise it to e. And we do this all mod n, by the way. We send it to Alice. And these are all public values. N is public, e is public. Obviously, Bob knows his own message. So this is all good. And Alice can now compute c to the d and recover the message. And only Alice can do this because only Alice knows little d and phi of n. So remember, right? Modular arithmetic is arithmetic done using remainders. So if I have a is equal to b mod n, then equivalently I have, well, a is equal to b plus some multiple of n, right? This makes sense if I'm just taking a number and its remainder. Remember, b is a remainder. So if I do division by n, I get this. It doesn't actually matter what k is. We just know this relation holds. So similarly, since I know e times d is equal to 1 mod phi n, then I know e d is equal to 1 plus k phi n for some k. Does everyone follow? Is all good? Right. So let's just walk through this equation for why RSA works. So Alice computes c to the d. Well, what's c? Well, c is just m to the e. That's what Bob sent. We want to get m. Well, just using exponent rules, I get e times d, which I said is equal to 1 plus k phi n. And now just using rules of exponents, I get m from that 1 times m to the phi n k. But remember, we're doing this, all of this. Oh, that should say mod n, not mod p. My bad. L, yeah. That's what I get for making slides very late. This is mod n, not mod p. I'll fix that and re-upload. But the point is, remember what I said, anything to the power of phi n mod n is 1. So whatever that value is, m to the phi n, I don't know, I don't care. That's 1. And 1 to any power is just 1. Alice gets the message back. So this is how we can do cryptography using RSA. Everyone follow that? Does it make sense? You don't need to know why. If you want to know why the theorem works, you can look at the proofs and stuff. It's really cool stuff. Or take a course in number theory. But the point is, it works. Since we can encrypt and we can decrypt. So before I get into attacks, any questions? Yes.
We have like messages on and so therefore message shall represent.
Yeah, so what we'll typically do is, usually if we're doing really large messages, is we'll agree on some sort of scheme to split up the message into chunks so that when I don't lose any information. But it's a very valid point that if I have a really long message, like if I'm saying like paragraphs of text, then I need a way to split it up. And it doesn't really matter how you do that to a certain extent. There's actually attacks you can do if you know how these messages are padded and split up. Hussein wrote a challenge on that, but your padding challenge. And yeah. Mm-hmm. That's kind of what's happening. Like N is like this key exchange without interaction. You just publish N. It doesn't, because we presume that factoring N is hard. So if you publish it, we say like, okay, no computer is going to really be able to factor this. So it's okay if I had this public key. Is that kind of what you were asking? I think the splitting up is more common, but I'm not sure off the top of my head. I just think like rather than introduce multiple crypto systems, symmetric and asymmetric, just for simplicity, people like, let's just stick to one agreed crypto system for this exchange. But yeah. And like any crypto system for a CTF challenge, we want to attack this. So what are some attacks? Well, the primes are small. Remember, this all relies on large primes. Well, if primes are small, as you'll see in some of these challenges, then then we can just factor and brute force. I'm talking like really small primes. This appears in a couple of challenges. Smooth primes make their appearance again. If you have smooth primes, you can do other attacks on RSA. If N, in fact, is too large, and this kind of gets into what Nathan was saying earlier, if N is too large, there are attacks that you can do on the crypto system if N is extremely large. Hassan wrote a challenge on this. I think it's called "Are You Winning, Son?" It's a good challenge. I recommend it. It's actually a challenge from a fall CTF from I think 2021. Oracles kind of make an appearance. This is a very broad thing to say, but like we have Diffie-Hellman oracles in certain CTF challenges. We have oracles for RSA. This might have to do with, again, we're doing exponents. So we have, there's an equivalent notion of this double and add thing. If you have oracles based on that, you can see stuff. CryptoHack has some cool oracle challenges, and I've seen God knows how many oracle challenges in various CTFs. But I can't really say anything more specific because that just depends on the challenge author. Just a little fun thing. Ducks. Hussein showed me this yesterday. This presentation, which is linked here, is a wild read. But I'm just going to say, pro tip: don't store secrets in paste bin. This was this was used to break instances of RSA a while ago because people just called the internet before Amazon. Anyway, this presentation is it's a fever dream. But yeah, don't use pastebin, etc., etc. And like I said before, Google is your best friend. You're going to get really far just by using Google. But yeah. And just as a quick overview, it's like some of the higher level like overarching themes of cryptography. Often we see trade-offs in like if I'm on low cost implementations, I may lose security and or performance. There's a very much as you've seen a lot of things in real life, there's this very much of like we have three options, pick two. If I want high security and low cost, I'm going to lose performance. If I want low cost, high performance, I'm going to lose security, et cetera, et cetera. These are things that cryptographers and hardware engineers have to deal with all the time, especially in like actual physical hardware implementations of crypto systems. And now like this is just like the very surface level of what cryptography is. There's a lot of stuff out there, right? You have things like signatures, hashing, making sure messages, like verifying senders and receivers of messages. You have like block ciphers, which I didn't get to. You have all these things. Cryptography is a huge field. There's so much to look into, which I'll hopefully cover in like future semester, in like future meetings way later. But yeah, that's it. Next meetings, like I said before, this Thursday is Rev 2 with Richard. Be really cool stuff. Z3 is amazing. It actually comes up with some cryptography challenges. And then we have this research presentation next Sunday, which I'm really looking forward to. Stealing hospital information. That's a cool tagline. So we come see what all of that's about next Sunday. But yeah, that's it. This is a long meeting. Sorry about that, but thank you so much.